Today we will learn about chapter 2, the amino acid, the building block of the protein. Chapter 2 is composed of 8 subjects, starting from the 20 amino acid, and also we will learn about acid-base property of amino acid, and also we will learn the stereochemical representation of amino acid, and also we will learn about peptide bond, and finally we will learn about stereoisomerism. Okay. So in this slide, I will explain the first subject, the 20 amino acids found in the proteins. So what is amino acid? So amino acid includes the 20 amino acid starting from the glycine, the alanine, and leucine, isoleucine, and something else. So we will see some details in the next slide, okay? And usually the amino acid exists in deuterium status. In Korean, we call it as 양쪽 이온 상태. So this is deuterium, this is amino acid. Figure 2.1 shows that skeletal model of generalized amino acid, showing the blue is amino group and the red is carboxyl group. So they have the plus charge and they also have minus charges. This plus and minus charge is enable the charged interaction, so it will make the crystalline lattice structure. So this is one example of crystalline lattice structure. So one amino acid and the other amino acid on one amino acid and the other amino acid. So this is also another example of crystalline lattice structure. This is the sodium chloride. Sodium is plus charge and chloride is minus charge, and they usually make the crystalline lattice structures. And that's why the amino acid show that higher melting and higher boiling points, because they always make the crystalline lattice structure. So they are very stable. The protein and amino acid, they are chemically or they are structurally very stable. So in this slide, we will learn the amino acid characteristics. Okay, to understand amino acid characteristics, we have to understand Henderson-Hasselbalch equation. So Henderson-Hasselbalch equation is equilibrium between the weak acid and its conjugated base. Okay, so because we already learned that the amino acid function as they have the carboxyl group, and they partly function as the acid, weak acid. So usually the equilibrium between the weak acid and its conjugated base allows the solution to resist change to pH when small amount of strong acid or strong base are added. Okay, so in this cases the protein solution pH start from around 1 or 2, start from here. So when we added the NaOH, this is strong base. So between this is the x-axis is the sodium hydroxide amount. So between the 0.01 or 0.09, even though we added NaOH, they did not change their pH very abruptly. Okay, just they show some plateau, very equilibrium status. This is why, because the protein is function as weak acid. So they have they show the equilibrium here. Okay, so in these cases, we can estimate the pH of the buffer solutions. Okay, so let's start from the Henderson-Hasselbalch equation again. So protein function as a weak acid, and after that it can donate H plus. It can dissociate with H plus and A minus. So A minus is function as its conjugated base. So K is we call it as the acid dissociation constant. K is the HA versus H plus and A minus. Okay, so in this cases log K is log like this. Okay, so we can change it. This equation is log H plus and log HA versus A minus. So after that we can change the location. So it means that minus log H plus and minus log K plus log HA versus A minus. So in these cases, minus log H is pH and minus log K is pK, and after that log is the HA versus HA minus. So this is pH. So because we already know the K constant, acid dissociation constant, so we know that we already know that each amino acid pKa number. So we already know the K number, so we can estimate the pH based on the amount of HA and based on the amount of the A minus. So okay, so the reason why we can estimate the pH because the amino acid function as weak acid. Okay. In previous slide, we found that amino acid function as the weak acid. So they showed that Henderson-Hasselbalch equilibrium like this. But the amino acid has the carboxyl group, and the amino acid also has the amino group. So they have the different pK number. pK is, we already learned that this is the acid dissociation constant. Okay. So for example, let's start from the alanine. So this is the alanine. So this structure is alanine. In the R group, they have the CH3 methyl group. For example, the pK1 is that 2.4. So this one, the alanine's pK1 is 2.4, and pK2 is the 9.9. So near the 2.4 pH, they show that some plateau equilibrium, and also near the 9.9, they also showed the equilibrium. Okay. Okay. So this is the titration curve, and so people add the sodium hydroxide. So they add the strong base. Okay. So in these cases, they show that one equilibrium. After that, they also show that another equilibrium. Okay. So below the pK1, so when the pH is around 2, the amino acid structure, they show that like this. Around the carboxyl group they show that OH, and the amino group, they have the NH3 plus. So this is their status. Around the pH 7, because pK1 is 2.4, so after 2.4, so the carboxyl group H is can be dissociated. So they will show that the carboxyl group show that minus, and the amino group is still plus. Okay, and at 9.9, so around the pH 12, they will show that this H plus is dissociated. So they only show the carboxyl group is minus, it's NH2, N is the, they show that neutral, NH2. So this is the, around the, according to the pH, they show that the different type of the status like this. One is the total charge is the plus, and total charge is 0. Total charge is 0, and total charge is minus, is like this. Okay, so usually the, for example, alanine, they only have the pK1 and pK2, and because they only have the, in R group, they only have the CH3. But some another arginine and aspartic acid and glutamic acid, in the R group, they also have another charge, so they all have the pKr, another number, pKr. Okay, so this is titration curve, and Pi in this case, when they have only pK1 and pK2, so Pi is the pK1 plus pK2 divided by 2, like this. In this slide, we will see another amino acid titration curve. Okay, this is the histidine. For example, this is histidine. Histidine has the amino group. They also have carboxyl group, and this is their R group. R group, they have positively charged like this. So in the case of the pKa value, pK value of the histidine is like this. So they have the pK1 is around 1.8, and also their pK2 is around 9.3, and their the pKr, because they have an R group, but R group is positively charged, so they have another equilibrium around at pH 6. So they have the pK1, they have one plateau region, and also they have another equilibrium. They also have the final equilibrium is like this. Okay, so based on this the titration curve. Okay, so when the pH is around 1.0. Okay, this is when the pH is 1.0. So their R group, their charge is like this. So amino group is the positively charges, and carboxyl group is the neutral, so like this. And also R group is also positively charged like this. So their status is like this, two positively charges. So pK1 is around 1.8. At the pK1, when the pH was around 5, so they passed pK1. After that, when the pH is around 5.0, okay, in this group is the carboxyl group is the dissociated. So they donate the H plus. So carboxyl group will become the COO minus. So in this case is the total charge is the plus minus is the +1. It's like this. So pKr is around the pH 6. After we pass the pKr, when the pH is around 8, so this is pH 8. When the pH is around 8, in this case is the R group. R group has positively charges. So this positively charges R group is R group. So in this R group is the H plus is dissociated. So they will become the neutral. Okay, and carboxyl group is still is minus. and this amino group is still positively charged like this. So total charge is the plus 0 is neutral. And pK2 is around 9.3. So after pK2, when the pH is around 13, okay, in this case is this is amino group. So H proton, H plus is dissociated from the NH3 plus, so it will become the NH2, so they will become the neutral, and carboxyl group will still be negatively charged, so their final charge will be -1. So this slide is summarized of the amino acid titration curve, so especially which has the R group. The R group has the positively charges like this. Okay. Previously we learned about titration curve in the alanine, but alanine they don't have the R group, but especially the histidine they have the another R group which has positively charged. That's why we can see the histidine status according to the pH. It's like this. Okay, +2, +1, 0, -1. So in this slide, I will explain the second subject, stereochemical representation of amino acid. So this is the amino acid structures. So amino acid is composed of 20 amino acids. Among 20 amino acids, 19 amino acids show that the generalized amino acids, the structure is like this, which has the containing the amino group is blue. So blue is amino group, and the carboxyl group is red, is carboxyl group, is like this. Okay, and also R group is attached to the center or the alpha carbons like this. So R group is attached to the alpha carbon. Okay, so okay, but another one amino acid, we call it as proline, has unusual amino acid which has a ring. This ring we call it as the 5 members. 1, 2, 3, 4, 5 members pyrrolidine rings. So we call it as pyrrolidine rings. So only amino acid, we call it as proline, has this kind of ring structure. Okay. So in this slide, I will explain the third subject, the peptide bonds. So we already learned the peptide bonds several times. So what is peptide bonds? So what usually the peptide bonds is initiated between the carboxyl group and the amino group. So finally, the water is taken out and they will make the peptide bond. So actually this amino acid is glycine and this amino acid is the alanine. So between the glycine and alanine and peptide bond is formed. So the glycine and alanine react together to form the dipeptide glycylalanine. So the important peptide bond is shown in red, is like this. And so this is dipeptide. How about the polypeptide? So this is polypeptide. So the N means that where the N is open to 50 and 300. So usually the polypeptide site is very bigger. So okay, in this case we also can see the peptide bonds here between the CO we call it as carbonyl and also NH. So between carbonyl and NH there is the peptide bond is formed, and also between the carbonyl and also NH there is a peptide bond is formed. It's like this. Okay, so in this slide I will show you the fourth subject, properties of the peptide bonds. So usually the peptide bonds is the usually the C-N bond, actually between the C and between the N is the 1.45 angstrom. However, when we measure the peptide bond, we found that actual size of the peptide bonds is about 1.25 angstrom. Why this kind of phenomenon is happen? Because between the carbon and nitrogen, usually there is a partial double bond is formed as a result of resonance. For example, this the carbon, and between the carbon and nitrogen, so usually the partial double bond is happen. So they will show like this. So between the carbon and nitrogen, so usually the partial double bond is formed by as a result of resonance. So in this case is it restrict. So in this case is it restrict the CN bond rotation. For example, CN bond, so rotation is restricted. CN the rotation is restricted. However, the bond between the carbon and the carbon, so we call it this carbon as C alpha carbon, and actually we call it as this carbon as C beta carbon. So between the C alpha and C bond, and between the N and the C alpha, this bond is rotatable. So this bond is rotatable. But this bond is also rotatable. But between this C and N, this bond is fixed. So because this bond is rotatable and this bond is rotatable, so usually the peptide is existed in cis and trans configuration. Okay. So from this slide, I will explain the fifth subject, the chemical and physical properties of amino acids. So I will explain the 20 amino acids, chemical and physical properties. Okay, let's start from the glycine. So glycine is the simplest amino acid. It only has H as a side chain. Okay, usually this is the backbone of the amino acid. They have the amino group and they have the carboxyl group, and they have the H and they have R group as side chain. But in the case of the glycine, they only have the H as a side chain. So glycine, we call it as G. The code, we call it as G. Okay. So in the case of the glycine, because they only have the H as a side chain, so this bond, the bond between C alpha and the C, this bond, and the bond between nitrogen and C alpha, this bond is easily rotatable. So how about when the R group is very bigger? In the case of the phenylalanine, in this case is the R group is very bigger like this. In this case, this bond is not easily rotatable. Okay. Okay, so now you have to write down the chemical structure of the glycine here, and you have to memorize the simplest code G. So when you go to the company, so we did not call glycine, we just call it as G. So if you hear the G, so you have to think about this structure. Okay. Okay. G is they have the very simple. G is the simplest amino acid, and they only have H as a side chain. Okay. So you have to memorize the structure, and you also have to memorize G. So in the middle term exam, so you have to write down the chemical structure of each amino acid, and also you have to memorize all of this code. Okay. So in this slide, I will explain the amino acid which has the aliphatic side chains. Okay, what is aliphatic? So aliphatic means that an organic compound containing only carbon and hydrogen joined together in straight chains. For example, CH3 is only composed of carbon and hydrogen. They joined together in straight chains. So this is, we call it as aliphatic side chains. Okay, the amino acid which has the aliphatic side chain is alanine, includes alanine and valine and leucine and isoleucine. So we will see some details. Okay. So the alanine, so we call it as alanine, and the simplest code is A. So you have to memorize A. Okay. And also their structure is they have, this is amino group, and this is carboxyl group, and this is the R side chain. They have the CH3. They have the aliphatic side chains. So because they have the aliphatic side chain, so they are chemically inert and chemically inactive, and they also show that hydrophobicity. So for example, this is membrane proteins. So inside the membrane, so this amino acid is the hydrophobic protein. So a hydrophobic protein is located inside of the lipid bilayer. So most of the protein is alanine or valine or isoleucine or is something else. So they are, how about here? This is the hydrophilic proteins. This is also hydrophilic protein. We will see some details in the later. Okay. So you have to memorize the structure. You have to write down this structure here, 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 and you also memorize the alanine is A, like this. So when you call it as A, you have to think about this is A is alanine, and also you have to think about the structure, because alanine has the aliphatic side chains, so it will be the chemically inert or chemically inactive, and they will show the hydrophobicity. Okay. So next is the valine. Valine is also, they have the aliphatic side chain, which is only composed of the carbon and hydrogen, like this. So for example, alanine, they only have the methyl group, they only have one carbon, but the valine is they composed of the 3 carbons like this. So the valine is also, because they only have the aliphatic side chains, so they are chemically inert and inactive, and they show that hydrophobicity. So valine, the structure is like this. They have the amino group, they have a carboxyl group and H. In R group, they have a CH and CH3 and CH3. And the simplistic code is V, it's like this. So when you call it as V, so you have to think about valine, and also there you have to think about the structure. Structure is they have the 3 carbon, it's like this, CH, CH3 and CH3. That's why they are chemically inert and chemically inactive. They show the hydrophobicity. So in blank region, you have to write down the valine structure, and also you have to write down the V is like this. Okay. Let's go over to the leucine. Leucine is also, they have the aliphatic side chains. For example, they have CH2, CH, CH3 and CH3. They only have the composed of carbon and hydrogen. this side chain, they are only composed of the carbon and hydrogen. That's why we call it as this is aliphatic side chains. Okay, so this is leucine. Leucine has the 1, 2, 3, 4 carbon. Okay, and we call it as the simplest code. We call it as the L, because they are only composed of the aliphatic side chains. They are also chemically inert and inactive. They show that hydrophobicity. So in all of the hydrophobic region, we'll easily see the alanine and also valine and leucine. Okay. Now we have to know some terminology. One is what is methylene, what is methane, what is methyl. And also you have to understand some carbon name. So this carbon, we call it C alpha, C beta, something like that. Okay, let's start from here. So okay, the leucine has they have aliphatic side chains. First one, they have CH2. So this CH2, we call it as methylene. How about this one? They only have a CH, only one H. In this group, we call it as methane. How about this one? When they have a CH3, we call it as methyl. So okay, the leucine has first they have a methylene group. Methylene means the CH2. After that they have the methane group, CH. After that we have the 2 methyl group. It's like this. How about the valine? Valine they have the methane group, and they have the 2 methyl groups like this. This is valine. Okay, and also we have to know the carbon name. So this is amino acid. They have the amino group, and they have carboxyl group. They have H, and in the side chain they also have carbon. So we call it as this carbon as C alpha carbon, and this carbon we call it as C beta, and this carbon we call it as C gamma carbon. How about this one? We call it as a C delta carbon. After that, if they have additional carbon, we call it as a C epsilon carbon. And finally, they have another carbon. We call it as a C zeta carbon. So first we call it this one. We call it a C alpha carbon. So previously we learned that here several times. We learned that this one we call it as a C alpha, and this is we call it C nitrogen, and this one we call it as a C alpha. So if they have this is the glycine. If they have the alanine, this H will be the CH3. So this one will be the C alpha, and this C will be the C beta. Okay. How about here in the valine? This is the C alpha, C beta, and C gamma carbon. Okay. So okay, in this C alpha, C beta, C gamma carbon, and C delta carbon, C epsilon carbon, C zeta carbon. Okay, so leucine has the inside chain. They have one methylene group, one methane group, 2 methyl group is like this. Okay. How about isoleucine? Isoleucine is the isomer of the leucine. For example, leucine, they have CH2, they have a methylene group. After that, they have a methane group. So in this slide, I will explain the final amino acid which has aliphatic side chains. The name is isoleucine. So isoleucine is isomer of leucine. So previously we learned leucine. The simplest code of the leucine is L. you have to memorize L. Now is isoleucine. The simplest code is I instead of the L. This is I, and they are isomer of leucine. So this is the leucine structure. This is the isoleucine structure. So they have the aliphatic side chain. So this aliphatic side chain is exactly similar. The chemical composition is exactly similar, exactly same, but their structure is a little bit different. So they are isomer. Okay. For example, in the leucine, they have a methylene group, they have a methine group, they have two methyl group. How about here? How about isoleucine? They have a methylene group. This is, and also this is the C alpha, C beta, C gamma, C delta. Okay. For example, in the C beta, they have the methylene group. They have a methine group. They have a CH. And C gamma, one is methyl and one is methylene. And C delta, they have the methyl group. But in case of the leucine, they have two methyl group. But in the case of the isoleucine, they have only one methyl group. Okay, so isoleucine is isomer of leucine. So that's why they are chemically inert and also chemically inactive, and they also show the hydrophobicity. Okay, so aliphatic side chain is the final amino acid which has aliphatic side chain is isoleucine, is isomer of the leucine, and exactly the chemical composition is exactly same, but structure is a little bit different. They have the isomer, and for example, they have the one methine group, and also their C gamma is that one is methyl and one is methylene. C alpha, beta, gamma. Alpha, beta, gamma. How about the alpha, beta, gamma, delta? They have the C delta. C delta is existed as only one methyl group in the isoleucine, but in the leucine, C delta is they have two methyl group exist. Okay. So from this slide, I will explain the amino acid which has the hydroxyl group. Okay, they have the serine and the threonine. Okay, let's start from the serine. So serine they have the nearly similar structure to the alanine. The alanine they have a CH3, but instead of H, they have the OH group. That's why the serine is not aliphatic side chains. So we already learned the terminology. Aliphatic side chain means that an organic compound containing carbon and hydrogen joined together. But in this case, instead of the hydrogen, they have the OH. So this is, we call it as serine. So serine's simplistic code is S. So you have to memorize the S, and you have to memorize this structure, because they have, instead of they have the OH, they are chemically active, and also they are hydrophilic. So you will see, for example, serine, you can see the location around this outside, this region, maybe in this region and this region, you can easily see the serine. Okay, and also the serine, okay, they have the first carbon is that they have the methylene group. For example, the alanine is the first C beta carbon, is they have the methyl, but C beta carbon, they have the methylene group CH2. Okay. Okay, so you have to write down the serine structure, and also you have to write down S, and you have to write down serine structure, and you have to write down S here. Okay. How about next amino acid which has a hydroxyl group is threonine. Okay, so this is a threonine structure. The structure is nearly similar to the valine, but instead of the methyl group, so they have OH group. Okay, so because they have OH group, so they are chemically active and also they are hydrophilic. So in the case of threonine, so you also can find the threonine location around this outside the hydrophilic region and inside the hydrophilic region. So, okay, so in the case of the threonine, they have their C beta carbon, they have the methane group, and also their C gamma carbon, they only have the one methyl group. For example, in the valine, their C beta carbon is the methane. They are methane group. They are exactly the same as this one, but in the C gamma carbon, they have two methyl groups like this. So you have to write down the threonine structure here, and you also have to memorize T. So threonine, the chemical is nearly similar to valine, but instead of their methyl group, they have OH group. That's why they are chemically active and they are hydrophilic. You can easily see the threonine is outside here and inside here. Okay, so you have to write down here, and you have to write down T, and you have to write down structure here. You have to write down the simplest code T. Okay. So from this slide, I will explain the amino acid which has the acidic residue. So we call it as this is the aspartate, or we call it as aspartic acid, and also glutamate, or we call it as glutamic acid. Okay, so let's start from the aspartate. So aspartate, they have the side chain, they have a CH2, and after that they have carboxyl group, COO-. Okay, they have the carboxyl group. Okay, so if you see here the aspartic acid, another name of aspartate, we call it as aspartic acid, and the pK1 is the 2.0, and pK2 is 9.9, and pKr, the pKr is 3.9. That's why this is the titration curve of aspartic acid. So because they have the pK1 around the pH, they have some equilibrium around the pH2, and they also have another equilibrium around the pH 3.9, and they also have a final equilibrium around the pH 9.9. Okay, so below the pH 2, their carboxyl group will be the COOH, and also their R group is there. They will have the carboxyl group. They have the OH. Their amino group is the NH3 plus. So that's why their net charge will be the plus. And when the amino acids located around the pH 3, because they are above the pK1, so this one, the carboxyl group, will be the COO-, so their net charge will be the 0. So when this amino acid is located around the pH 7, So there, the carboxyl group will be the minus, and this carboxyl group also will be the minus. So their total charge is minus, minus, plus will be the -1. So when this amino acid is located in around pH 12, so they pass the pK2. So it means that this carboxyl group will be the minus, and this carboxyl group is also minus, and this amino group will be there is no charges. So their total charge will be the -2. So when we solve the problem set, okay, this is problem set. So which of the following peptides might be the positively charges or negatively charges or no charges? So in this, when you solve the problem, so we have to assume that amino acid is located in the pH 7. Okay. So for example, the aspartate, the net charge will be the -1, not 0, not +1, not -2. So we have to assume that amino acid is located in the pH around the pH 7. So will be the aspartate net charge will be the -1. Okay. So now in here, so you have to write down the aspartate, the structure, CH2 and carboxyl group, and also write down the simplest code D. Okay, because the alanine has their alanine simplest code is A, but the aspartate alanine already used the A, so aspartate used the D as a simplest code. And so because they have the carboxyl group, so they are acidic. So because their pKr number is around the 3.9, so they are acidic. So in this slide, I will explain the glutamate. So glutamate also has the acidic residue. They have the R side chain, R group. They also have carboxyl group. Okay, so this is another name of glutamate. We call it as glutamic acids. So their pK1 is 2.1, their pK2 is 9.5, and their pKr is 4.1. Okay, so and their net charge at the pH 7 will be the negative charges. Okay. Okay, so because they have the carboxyl group and their pKr is 4.1, so they are acidic. Okay. Okay, let's start from the glutamate. They have the methylene group CH2. They also have additional methylene group CH2, and there are C delta carbon. Their C delta carbon is that they are the carboxyl group. So their C beta carbon is they have the methylene group, and their C gamma carbon they have the methylene group, and their C delta carbon they have a carboxyl group is like this. So they are acidic. Okay, so glutamate, the simplest code is E. So usually so how about they use the G, but the glycine use their simplest code as G. So because the glycine used the G and glutamate used E, so glutamate is E. So if we call it as E, so you have to think about glutamate, and you also have to think about the glutamate structures. Okay. Now you have to write down here and here and here the glutamate structure, and you have to write down E, and there the pH their net charges around at pH 7 will be the -1. Okay. Okay. So in this slide, you will see the amino acids which containing the amide group. So this is carboxyl group. Actually, this is the amide group, which has the carbonyl, carbonyl C, CNO, and NH2. So this is the amide group. So the first one is asparagine, and second one is the glutamine. Okay, how about start from the first one? The first one is the structure is nearly similar to aspartate or aspartic acids. So this is the asparagine. So the simplistic code is N. It's because they have N, the simplistic code is N. So you have to memorize the N, and also structure is nearly similar to aspartate except for amide group. So how about the pK1 and pK2? So pK1 is about 2.1 and pK2 is about 8.7. But in the case of the amide group, the pKr, they don't have the pKr numbers like this, because this is not positively or is not negatively charged. Okay, so the asparagine is, they have the methylene group, and their C gamma has the carbonyl O and the NH2. Okay, so you have to write down here the asparagine structure, and you have to write down N. Here you have to write down the asparagine structure, and you have to memorize the N. Okay. Okay. So next amino acid, we call it as glutamine. So glutamine is also has the amide group. Their structure is nearly similar to the glutamate, except for glutamate has the carboxyl group, but the glutamine has the amide group is like this. Okay, and so we can see the pK1. The pK1 of the glutamine is about 2.2, and pK2 is about 9.1. So even though they have the R group, the pKr, they don't have the number. Okay, because they are not positively charged or they are not negatively charged. Okay, so there, this is C alpha and C beta, C gamma, C delta. Okay, their C beta is that they have the methylene group. They also have a methylene group. Finally, they have the carbonyl, and also they have amide. So this is the amide group. Okay. Okay. So in this slide, I will explain another amino acid which is containing the amide group. We call it as the glutamine. The glutamine structure is nearly similar to the glutamate, except for glutamate has the carboxyl group, but glutamine has the amide group. So glutamine's the simplistic code, we call it as Q, because glycine used the G, so instead of G, glutamine use Q. Okay, and also the pK number is glutamine is they have the pK1 is 2.2 and pK2 is 9.1. Okay, so they have the carbon beta has the methylene group, and carbon gamma they also have the methylene group, and finally they have the amide group is like this. Okay, so you have to write down the structure of the glutamine here, and also glutamine here, and write down the Q. So you memorize Q, and also you memorize the glutamine structure is like this. They have the amide group and their structure is nearly similar to glutamate. Next, we will learn about amino acid which have a sulfur group. Okay, the first one is a cysteine, and the other one is methionine. Okay, so we will start from the cysteine. Okay, so cysteine has the sulfur group. Okay, they have the reactive thiol group. So SH is the thiol group, so they have the reactive thiol group, SH. The structure of the cysteine is nearly similar to serine. Serine has the OH, but the cysteine has, instead of the OH, cysteine has SH, and the simplest code of the cysteine is C. They use the C. Okay, so you have to write this is structure. They have the amino group, and also they have a carboxyl group. In the R group, they have the CH2 and SH. And this cysteine plays an important role in the formation of disulfide bridge like this. And cysteine they meet each other, and they always make their forms disulfide bridge. So we can easily see this disulfide bond in the antibody, because the antibody is composed of 2 heavy chain and 2 light chain. 2 heavy chain is connected by the 2 disulfide bond, and also 1 heavy chain and the other light chain is also connected by disulfide bond, and also 1 heavy chain, the other light chain is also connected by disulfide bond. So here there will be the cysteine, and here there will be the cysteine. Okay, so you have to write down cysteine structure and also memorize C. Cysteine structure, and you have to memorize C. Cysteine structure, you have to memorize C. Okay. So in this slide, we will see another amino acid which containing the sulfur group. So this is the methionine. So this is the structure is like this. They have a C alpha and C beta and C gamma. So instead of the carbon, they have a sulfur. Finally, they have a methyl group is like this. So they have a methylene. After that, they have sulfur. And finally they have the methyl groups. So usually in the methionine is that the simplistic code is M. Okay, and also this sulfur can be easily oxidized and to form the sulfoxide. So S can be oxidized like this. And also sulfoxide is also can further be oxidized like the sulfone, like this. CH2, SO, and SO is like this. So usually the methionine is S. Methionine contains the S, so, and this sulfur can be easily oxidized to form sulfoxide and the sulfone. So figure 2.19 to show that oxidation of methionine side chain by strong oxidizing agent. So methionine, the S, can be the sulfoxide. Finally, when they were further oxidized, they will become the sulfone. Okay, so you have to write down the methionine structure here, and also write down M. And you also write down the methionine structure, memorize the M. Okay. So in this slide, we will see the amino acid which has the basic residue, especially the amine group. Okay, one is lysine, and the other one is the Okay, here the other one is arginine. Okay, so we will start from the lysine. Okay, lysine has the amino group. Okay, this is R group. They have a CH2 methylene group, methylene group, methylene group, methylene group. Finally, they have the amine group, NH3 plus. So usually the pK1 is about 2.2, pK2 is about 9.1, and pKr is about 10.5. Okay, so this is pK1 is around 2.2, and pK2 is about 9.1, and pKr is about 10.5. Okay, so below the pH2, below the pH2, carboxyl group is the CO and OH, and they have the amino group, and they have amino group, and total charge is about +2, plus the total charge is about +2. How about around the pH7? At pH7, carboxyl group has around here, carboxyl group they donate the proton, so they will become the COO minus, so charge will be the minus, and this one will be the amine group as they have positive charges, and this amine group they also have positive charges, so total charge is +1. Okay, and around the pH 10 will be the total charge is 0, and finally above the pH 13 or 12, so total charge will be the minus. Okay, so this is the lysine. So lysine residue is the lysine is the simplistic code is K. So they have the amino group at the end. So the pKr is about 10.5. So they show that they are very basic. Okay. So you have to write down here the lysine structure, and also to write down the K, the simplistic code. So because the lysine used the L, so lysine cannot use the L, so lysine instead L, lysine use K. So you have to write down K, and also write down the lysine structure here and here. Okay. So in this slide, we will see another amino acid which has the basic residue. We call it as arginine. Okay. So this is the arginine structure. They have the inside chain. They have a methylene, and they have the guanidine group, which is composed of the 3 amine. Inside there, they have the carbon. Okay. So they have the pK number is that their pK1 is about 1.8, and pK2 is 9.0, and their pKr is 12.5. So arginine has the guanidine group, and they are most basic side chains because their pKr number is 12.5. Okay. So this is the guanidine group. Figure 2.27 to show that charge delocalization and isomerization within the guanidine group. Okay, so this is the initial structure of guanidine group, which has the NH, and in the center they have a carbon, and they have the NH2, and this NH2 is positive charges. But in this case, so carbon between the carbon and nitrogen, and double bond is made, and after that this will become the positive charges. Or in these cases, the carbon and nitrogen become the double bonded. After that, this one become the positive charges like this. So guanidinium group, usually they show that charge delocalization and isomerization is happens within the guanidinium group. Okay, so the simplistic code of arginine is R, because alanine used A, so they cannot use A, so arginine use R. So you have to write down here the arginine structure: CH2, 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 NH, C, amine, and amine. One of them become the positive charges. Okay, so you have to write down here, 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 and also write down the R, 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 R. Okay. In this slide, I will explain the proline. Proline, so among 20 amino acids, 19 amino acid has the regular structure. The only proline has a ring structure. The ring, we call it as cycline or pyrrolidine. This is, we call it as pyrrolidine ring. So they lack reactivity. Okay, so this is the they have the carboxyl group and they have amino group. Okay, so they have the additional the CH2 and CH2. Finally, they have CH2 is like this. Okay, so they have the cyclic pyrrolidine rings. So they don't have any charge, and also they lack the reactivity. So usually this is the regular amino acid polypeptide structure, starting from the N-terminal region and ends with the C-terminal region. So their direction is just like this, like this. But in the case of where the proline is existed, so the direction is like this. But sometimes when the proline exists, they change the direction, or they change the direction like this. Okay, this is the cis form and this is trans form. So we will see some details in the chapter 3. Okay, the important thing is the proline is the simplistic code is P. So they have the cyclic pyrrolidine rings because they don't have any charge, so they lack reactivity. So you have to write down here, 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 the proline structure, and write down the P. You have to memorize the P. So usually when the proline is exist, the direction, the amino acid polypeptide direction is changed like this, or like this. Okay, so this is a regular polypeptide structure starting from the N-terminal region to C-terminal region. But when the proline exists, the direction is changed. Okay. So in this slide, we will learn about histidine. Previous, we learned about the histidine's titration curve, and they have the pK1, and they also have a pK2, and they also have a pKr number. So because they have this R group, they have the plus NH, the plus charge. So their pKr number is 6.0. So based on the pH, when they were in the pH 1, their charge is plus and plus 2. So pK1 is around 1.82. So when they were in the pH 5.0, their charge is the plus minus means they're plus 1. How about the pH 8? Or how about pH 7? So their charge will be the plus minus will be the total is 0. Okay, so we have to know that at pH 7 their total charge is the 0. Okay, so we have to know this value. Okay, So histidine has the imidazole ring is like this. So this is imidazole ring composed of the 2 carbon, and also they have the NH. Finally, they have the CH. So this ring we call it as the imidazole ring. So figure 2.33 show that the localization of charge in protonated imidazole side chains of histidine. Okay, for example, in this case, plus charge is located here in this amine group, but this plus charge can go to this one. Okay, in this case, double bond is here, but the delocalization is happens. So in this case, double bond is moved to the here. So that's why this nitrogen can be the positively charged. So okay, so this is the histidine structure. They have the carboxyl group, and they have amine group. In the R group, they have the methylene, and they have the imidazole rings. Okay, so the simplistic code histidine is H. So we have to memorize H, and also we have to memorize the structure. Okay, once again, the structure, the R group is composed of methylene, and also they have the imidazole ring. So imidazole ring, they have the carbon and carbon. Between carbon and carbon, there is the double bond is located here, and they also have NH. Finally, they have CH. So between the C and this can be the double bond, and this can be the plus charges, but the localization can be happen. So this bond can be double bond, and this can be the plus charges like this. Okay. In this slide, I will explain the final amino acid which has the aromatic residue, which has the penyl ring. One is the start from the phenylalanine and tyrosine and tryptophan. So these 3 amino acids usually observe UV region of the electromagnetic spectrum. So this is electromagnetic spectrum include the UV and visible light. Okay, so usually these 3 amino acid observes in UV ultraviolet UV region. Okay, and the epsilon means that this is the epsilon. Okay, epsilon means that the molar absorptive coefficient. It means that indicates how much light is observed at a given wavelength. For example, is phenylalanine around the 260 nanometer. Their coefficient is about 200. How about tyrosine? At around the 280 nanometer, their epsilon number is about 1,400. But the tryptophan is the largest amino acid, and around the 280 nanometer, their epsilon number is about 5,600. Okay, so we will see some detail in the next slide. Okay. Okay, so let's start from the phenylalanine. So phenylalanine, we call it as F. Okay, the simplest code is F. Okay, so this is phenylalanine. They have a carboxyl group, they have an amino group, and also they have the methylene, and finally they have the phenyl ring like this. Okay, so this is, we call it as the phenylalanine. Okay, so phenylalanine is, they have the C alpha and C beta. After that they have the C gamma, C delta, C epsilon, something like that. So okay, this is the C alpha, and this is the C beta, C gamma, and this is C delta, C epsilon, and C zeta. So for example, in this this hydrogen, we call it as the HB, and also this one, they don't have any hydrogen. In this one, we call it as this carbon, we call it as carbon delta, and also the hydrogen is hydrogen delta. This one is carbon epsilon, and hydrogen is hydrogen epsilon. How about this one? This one is, we call it as a carbon zeta, and this hydrogen is the hydrogen zeta. Okay. So this is the structure is nearly similar to the alanine, but alanine has this location, they have H, but the phenylalanine, instead of H, they have the phenyl rings like this. Okay. So you have to write down the phenylalanine here, 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 and also you have to memorize the F. Okay, F, 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 F. Okay. So next is the tyrosine. So tyrosine is exactly similar to the phenylalanine, except for the phenylalanine. They have here they have the hydrogen. But instead of hydrogen, tyrosine has the hydroxyl. They have the OH group. So this hydroxyl, this is the OH, this side chain. This hydroxyl group makes tyrosine more reactive with other substances. Okay. For example, phenylalanine is not reactive with other substances, but because see here, they don't have any charges. But tyrosine, they don't have any charges, but they have the hydroxyl, OH group. This OH group makes tyrosine more reactive with other substances. So we have to memorize tyrosine. So tyrosine is the simplistic code is Y. So we have to memorize Y. So write down the tyrosine structure, and we have to memorize simplistic code Y. Y. Okay. So in this slide, I will explain the final amino acid which has the aromatic residue. Okay, the name is tryptophan. So tryptophan is the largest side chains. So this side chain, they have the methylene group. After that, they have the indole side chain. So we call it as this ring as the indole ring. Okay, so they have the carbon, and they have the NH group, and they have carbon. So this ring, we call it as the indole ring. So the tryptophan, it has the largest side chain and also has the highest molar absorptive coefficient. For example, the phenylalanine, the epsilon number is around 200, tyrosine about 1,400, but tryptophan, the epsilon number is 5,600, because they have this indole ring, so they observe the UV length is UV light is UV is very well. So this is the tryptophan, the largest side chain, and they have the indole ring. Okay, so the simplistic code is W. So they have the carboxyl, they have amino group, they have the methylene. After that, they have the indole rings like this. So this is the nitrogen. Okay, so this carbon, nitrogen. Okay, this is the, after that they have the phenyl rings like this. Okay, so we call it as the tryptophan. and tryptophan has the highest molar absorptive coefficient. So the epsilon number is the highest. Okay, so you have to write down the structure tryptophan here, 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 and you have to write down W. Okay, W, W, W. Okay. So in this slide, I will explain how to quantify the amino acid or how to quantify proteins. So in this case, we used Beers-Lambert rules. So Beers-Lambert rule used the UV wavelengths, especially around the 280 nanometer. So we used this UV wavelengths, and this is the rule. The observance is that epsilon is the molar absorptive coefficient, and the C is the concentration in moles, and L is the light path length. This is a centimeter. Okay, so this is one example. So molar extinction coefficient. This is also same thing, same word. Molar absorptive coefficient of tryptophan is 5,800. But what is the approximate observance over 0.02 millimole solution when measured in a 1 centimeter light path? Okay, so this we have to calculate the observance. So the observance will be like this. So the epsilon number will be 5,800 multiplied the concentration was 0.02 multiplied, this is millimole. So we have changed it to the 10 minus 3 like this. Okay, after that, just the right path length is 1 centimeter. So finally the answer will be, so you can calculate it. Maybe the answer will be this one. Okay. So in this slide, I will explain the final subject, stereoisomerism. Okay, so there is two nomenclature methods. One is the DL nomenclature, and also there is another nomenclature is RS nomenclature. So previously we used DL system. Nowadays people use the RS system. Okay, in this slide we will briefly see the DL nomenclature system. So amino acids, in amino acid there are two configurations. One is the L configuration, the other is the D configuration. For example, this is the alanine. Okay, so this is the L configuration and this is the D configurations. So all naturally occurring amino acid shows that L configuration. Why do they have the stereoisomerism? Because they have the chiral center. Chiral center means that it contains 4 different groups. For example, in the L-alanine or D-alanine, both of them has the chiral center because this carbon has 4 different in this carbon, so it's connected by the 4 different groups. Okay, so usually when we put, for example, in the D-alanine, so to differentiate it where this amino acid is a D configuration or L configuration, so people put the sample is here. Okay, this is the light source. So normal light, they have the different direction, but people use the polarizer. So after the light past this polarizer, we can only see this plain polarized light. So after the sample is here, for example, D-alanine is here. After this plain polarized light meet the sample, in this case, D-alanine, they show that the plain polarization has been rotated at the right direction. In these cases, we call it as the D configuration. How about the L configuration? When we put L-alanine in the sampling tube, so when the plain polarized light meet the L-alanine, there the light is changed to in the left direction. So in these cases, we call it as the L configuration. Okay, so usually this is L configuration. So usually the carboxyl group is located in the right, and amino group is located in the left, and hydrogen is far away from here, and also the methyl group is in the upper location. When the pore group is located like this, usually they show that left direction. So we call it as this is L configuration, L-alanine. Okay. So in this slide, I will explain the stereoisomerism, especially the RS nomenclature system. Nowadays, the people usually use the RS nomenclature system to identify whether they are R isomer or whether they are S isomer. To do the RS nomenclature, first we have to identify chiral center. So what is chiral center? Chiral center contains 4 different groups. Okay, so this is chiral center. Okay, so usually we consider from the C alpha carbon. After that, we also consider C beta carbon. After that, we just consider C gamma carbon. After that, prioritize 4 groups from the 1 to 4. 1, 2, 3, 4. 1 is the highest and 4 is lowest. So, okay, this is raw how to prioritize the 4 groups. Okay, so each atom bonded to the chiral center assigned a priority by atomic number. For example, the hydrogen, the higher atomic number, higher priority. For example, if the H hydrogen is connected to the chiral center, so the H is 1. How about carbon? Carbon is 6, nitrogen is 7, oxygen is 8, S, sulfur is 16, something like that. So this is a priority 1, 2, 3, 4, something like that. Okay. After that, another way is the same atom bonded to the chiral center. So in this case, is the same atom. For example, carbon, 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 carbon. Same atom bonded to the chiral center. After that, we have to look to the next set of the atom. For example, next set of atom in this case is the H hydrogen. So in this case is the carbon. So in this case is the nitrogen. In this case is the oxygen. So it means that this is the priority 1, priority 2, priority 3, and priority 4. Okay. Okay. After that, usually the CH bond is the lowest priority, usually the pointing away from the mirror. So this H is pointing away from the beer. At that rank 3 remaining group according to priority. In this case, there is a OH and CH2CH3, and there is a methyl groups here. The priority starts from here, and second, third. So the ranking is when they 1, 2, 3 is the clockwise. They show the clockwise rotations. We call it as this is the R isomer. For example, in this case, they show that count clockwise. We call it as S isomer. Okay, so this is the method how to do RS nomenclature. Okay. This is the one example how to nomenclature threonine based on RS nomenclature system. Okay. First, we have to identify the chiral center. So in this case, is threonine. They have we usually start from the C alpha carbon. For example, C alpha carbon is connected by the carboxyl group, hydrogen, and amino group, and also connected to CHOH, CH3. Okay, they are different groups are connected to this C alpha carbon. So this C alpha carbon can be the chiral center. How about the C beta carbon? C beta carbon is also connected by hydrogen and carbon and OH and methyl. So in this carbon is also can be the chiral center. So threonine has the 2 chiral center. Okay. In this case, let's start from this C alpha carbon. Okay. So we have to, based on the C alpha carbon, we have to prioritize 4 groups from 1 to 4. So usually the CH bond is pointing away from the beer. So in this case, this is carbon. Okay, this the H is like this. So CH is far away from pointing away from the beer. After that, we see that this is a carboxyl group, and this is the amino group, and this is the CHOH CH3. Okay. What is the higher priority? Because the NH3, so N is the atomic number is 7, carbon is 6, and this carbon is also 6. So priority is this one. So this is the first one. How about second one? So this one or this one? Because in this case is the carbon, so we have to think about the next state of atom. But in this case is the next state of atom is oxygen and oxygen. So in this case, the next state of the atom is oxygen, OH, and CH3. So in this case, this carboxyl group has a higher priority, and this is the third priority. Okay. So in this case, the amino group is first, and carboxyl group is second, and the other group is third. So in this case, we found that the direction is the counterclockwise. So in this case, we call it as a SS. So in the case of we have the one more than chiral center. So we usually think that the carbon is this carbon which has the carboxyl group. So we usually assign the 1, and this carbon we usually assign the 2, and the next carbon, C beta carbon, we usually assign the 3. So in this case, the S is the 2S. So this is we call it as 2S. Okay. So next, we also have to think about the chiral center. Okay. So this is the C. This C is also another chiral center. Okay. So this is the C. And also there is the OH is located here, and methyl is located here, and H is located here, and the other carbon and the other group is located here. Okay. So first we have to prioritize 4 groups from 1 to 4. 1 is the highest and 4 is the lowest. First, we have to CH bond is pointing away. So CH bond is pointing away from the beer. After that, we have to rank 3 remaining group according to the priority. But in this case, the O is the atomic number is 8. So and also C is atomic number is 6. How about the C is also atomic number is 6. So in this case, they have the same C, but we have to think about next set of the atom. So in this case, the next atom is H, but in this case, the next atom is nitrogen. So it means that this is the higher, this group has higher priority than this one. Okay, okay. So this is the amino. Okay, this is the OH, methyl, and the other group. So in this case, this is number 1, and this is number 2, and this is number 3. The direction is the clockwise. So we call it as the R configuration. But the carbon number is the 1, 2, 3. So we call it as a 3R configuration. So in the case of threonine, we call it as they have the 2S, and also they have the 3R configuration. So in the midterm exam, I will show you this kind of configuration, and also I will show you this information. So you just have to identify whether this carbon, or whether, for example, whether this carbon is 2S or 2R, whether this carbon is 3S or 3R. Okay. So today we learned about 20 amino acids found in the protein, and so we also learned about several properties of the amino acid or peptide bonds. And the important thing in this chapter, we have to memorize 20 amino acid configuration, 20 amino acid structure and their simplistic code. And also we have to know how to quantify the amino acid. Finally, we have to know stereoisomerism, especially we have to understand RS system. Okay? So today we will finish class.